This is the fifth in a series of resources on integral calculus. We define the idea of an integral. We investigate the fundamental theorem of calculus and look at some basic rules for integrals. We explain the difference between definite and indefinite integrals, looking at a basic example. We consider using Riemann sums as a method for approximating a definite integral. We investigate the integrals for specific function forms, including polynomials and trigonometric functions. We will also look at substitution methods to simplify certain integrals. In the previous resources, we defined an integral as the area between the graph of a function and the x-axis on some closed interval. We then considered Riemann sums as methods for approximating this area. However, when we first started considering integration, we thought about it as a way to undifferentiate a function. In more precise mathematical language, we considered the integral to be the antiderivative. In other words, the process of finding an integral is to find some function, which we usually denote capital F of x, whose derivative is the function little f of x, that we are attempting to integrate. For example, suppose we want to find the integral from 3 to 8 of the function 4x with respect to x. As a first guess, we remember that taking a derivative lowers the exponent by 1. So our initial guess is that the antiderivative of 4x would be 4x squared. We need to take the derivative to make sure our guess is correct. If we take the derivative with respect to x of 4x squared, we end up with 8x. So our initial guess is twice as big as it needed to be. As an improvement, what if we guess the antiderivative to be 1/2 of 4x squared, or 2x squared? When we take the derivative of this function, we have the original coefficient 2 multiplied by the original power 2, and the exponent drops by 1. So the derivative of 2x squared is exactly the 4x we were attempting to integrate. So to find the actual integral, we find the function 2x squared evaluated from 3 through 8. Plugging in, we have 2 multiplied by 8 squared minus 2 multiplied by 3 squared. Completing the calculations, we find the area to be 110 square units. Can we generalize to find the integral for any polynomial function? If little f of x equals x raised to the power n, what is the antiderivative function capital F of x? As before, our initial guess is that capital F of x would be x raised to the n plus 1 power. To check, we will take the derivative with respect to x. Doing so, we end up with the quantity n plus 1 multiplied by x to the power n. To account for this, we improve our guess for the antiderivative to be 1 over the quantity n plus 1 multiplied by x raised to the n plus 1 power. Checking the derivative, we have 1 over n plus 1 multiplied by n plus 1 multiplied by x to the n. The n plus 1 and 1 over n plus 1 cancel each other out, and we are left with x to the n. So we have successfully found the antiderivative for a general term of a polynomial function. Let's take a look at an example and find the definite integral for a polynomial function. Suppose we want to find the integral from 7 to 10 of the function 3x squared plus 10x plus 7 with respect to x. Using the rule we developed, we have 1 over 3 multiplied by 3x to the 2 plus 1, plus 1/2 multiplied by 10x to the 1 plus 1, plus 7x evaluated from 7 to 10. Simplifying, we have x to the third plus 5x squared plus 7x evaluated from 7 to 10. We plug in and have 10 cubed plus 5 multiplied by 10 squared plus 7 times 10 minus the quantity 7 cubed plus 5 times 7 squared plus 7 times 7. Completing the calculations, we find that the integral with respect to x from 7 to 10 of the function 3x squared plus 10x plus 7 is 933.